Uh, Dear participants, thank you for joining this online dialogue event. It's organized by Klaipeda University on the topic of electric water mobility. The name of the event is Technologies and Development of Electric-Driven Ships and Boats. This event is organized in the framework of Interreg South Baltic project. The project name is to support South Baltic SMEs to enter the international supply chains and sales markets for boats and ships with electric propulsion. And the acronym is ELMAR. The goal of the event is to learn about latest developments in battery technology for marine application, wireless charging technology, and its application to boats and ships, electric drive systems. Also, we will learn today about innovative ship designs and about the results of the retrofitting process of X-Rescue boat into pure electric driven pleasure boat, which is done during ELMAR project period. So, as concerns the program of today, I will shortly share the agenda and today first we will start with Daniel Dorflinger from ITAC. He will speak about wireless technology, then following by Dr. Frank Deal from EOS Batteries, speaking about batteries with marine application. Then following with Dino Lancharic from Euronavis. The company is representing the electric drives and also supplies different parts and makes a project. Dino will explain by himself. Then following at 10:55 by Western Baltic Engineering is a design company which is busy also in the field of electrification of the ships. And the closing will be the presentation of green boats. That is the process of restoration of X-Rescue boat into pure electric pleasure boat. Then I will give now the word to Daniel. But I see that Daniel is at the moment away. He was saying that he can have some problem with internet. Hopefully, but I hope that nobody will be against if we maybe switch. Frank, can you take over?
Yes, I can.
Yes, and I will try to check with Daniel what is the
problem. All of a sudden he disappeared. Yeah,
yes,
I could see him already. Yeah. Okay.
Yeah. Well, thank you. The floor is yours, please.
Yes. Thanks. Thanks very much. Okay. Okay. Can everybody see?
Yes.
The screen. Okay. Perfect. Okay. Yes. Then. Yeah. A warm good morning and welcome as well from my side. Just to introduce myself shortly. My name is Frank Wiel. I'm the head of sales at EAS Batteries. We are producing battery cells, battery systems with a particular focus on marine batteries, and that's what I'm going to share with you in the next couple of minutes. So just a short introduction what EAS is about. EAS batteries already produces battery cells and battery systems since 1996, so that is now our 25th anniversary. And we always did this in the location in the center of Germany. And right from the beginning, it was a focus on lithium-ion battery cells and customized battery solutions. Yeah, over a couple of different steps, we had different investors. Nowadays, we're a part of the Monbad group. Monbad is the third biggest lead acid battery producer in Europe, based in Bulgaria, and that's our mother company. And this company actually supported us in developing a marine battery system, which I'm going to show a little bit more in detail later on. So what is roughly, let me just give you a short introduction and an overview which application fields we're targeting. So we have, from a cell perspective, quite a strong record in aerospace applications. So we provide cell and battery packs for example, for the Proton M launcher from Russia. Currently developing a battery pack for the new Vega launcher from ESA. We did some battery systems for landing applications like the one from Vertical Aerospace. We did also something in automotive, but only in niche automotive applications, as well as stationary. And there's also a pretty nice record already on cell level for leisure U-boats, as well as, and this is one of the most famous solar boats, solar vessels, which we staff with our batteries as well. This is the Planet Solar ship, which is still sailing around the world permanently, and already having the second pack of battery systems on board provided by EAS. So in terms of production technology, so as mentioned, we're doing cell and battery systems. So we start really from scratch. So we start from powder to cell. So we have our own electrode production. We do cathode and anodes ourselves. We wind them and make various cell types and sizes, but all based on cylindrical cell design. So this is where we come from. We're not doing pouch cells currently. And based on these cells, we make, let's say, customized battery solutions. To give you an overview about the technology where we are, you know, probably the typical picture for different battery technologies in terms of specific energy and specific power. The lithium-ion technology covers a wide area in terms of specific power and specific energy. EAS traditionally positioned themselves more in the area of high power cells, so high performing cells with high C rates and less in the area of high energy, which is typically covered by the mass producers and then batteries suppliers that go into the automotive industry. Yeah. But in principle, the technology in-house is there to make all types of cells. But I just want to emphasize that lithium-ion battery technology is, of course, a wide range, and we can cover basically everything. But as a starting point for now, we are on the high power range. So in terms of cell portfolio, this is a rough overview. It's all cylindrical cells in different formats. The two cell types on the right are based on an NCA technology, and this is the cells that we supply into the aerospace industry, for example. The main focus, though, currently is on LFP, lithium iron phosphate technology. Here we've got some cells like the 40 amp hour cell, the 50 amp hour cells, and a smaller one. It's the same diameter, but just a little bit shorter, a 22 amp hour cell. And this portfolio is actually, or basically these two, the 40 and 50 amp hour cells, are the main cells that we use in marine applications. So for marine applications, we decided not to go with the NCA technology. That has different reasons. First one is safety. Another one is cycle life. And the third one is all over everything around sustainability and availability of non-poison materials. So lithium iron phosphate is not having any nickel parts, no manganese, and of course no cobalt. So this is a pretty environmentally friendly technology as well. So taking an example of the 40 amp hour cell, this is the core cell that we are currently using for our battery system. In terms of market approach, I mean, this is probably a well-known picture. So the market for lithium ion batteries is permanently growing. Marine, rail, underground mining, this is particular markets we are looking at with a clear focus though on the marine vessels. So the solution we developed is called Easy Marine. And before we go into a little bit more detail on the system specifications and the system features, a system solution, I'd like to give just an overview what kind of a wide span actually marine applications have. That goes from spinning reserve, load reduction, peak shaving, to full electric ferries, hybrid systems, hybrid ferries, electric cranes, so everything around port infrastructure and materials handling. So, and of course, as always, there is no one solution that fits all. So for full electric ships, for example, the classical case is start in the morning, discharge slowly, and recharge and charge overnight. That's a typical high energy application. So you need a high energy dense cell. Power performance of the cell is, let's say, second priority. But that's a typical classical full electric ship application. If we go more into specific stuff like fall right through on a hybrid system, spinning reserves, load leveling, or shore stations for charge, for fast recharge, everything around peak shaving or energy recapture, and finally, flexible dynamic propulsion. The more we go in that direction, the more high power and power performance in cells play a crucial role. Let me just give one comment on the full electric. Full electric does not necessarily mean that there is always a need for high energy only. If you imagine you've got a commute ferry, which is opportunity charged in between the days. So then you may have slow discharge rates, but you have probably high charge rates. In this case, you definitely need at least a medium or even a high power battery solution. So full electric does not necessarily means always only high energy densities. So even in this particular cases, you may need really power performing systems. So as an example, marine electrification. So ferries are a typical business where hybridization starts. The leading country, this is also well known, I think, is Norway. So, and if we look to the typical vessel types and the different segments of marine applications, we see that most segments are not really addressed currently. So there's a huge potential for doing much more with battery systems on board of ships. So, as our focus is mainly on a hybridization of systems, so that we are not particularly looking or exclusively looking into full electric systems, we are looking more on the hybrid systems because this is where medium power or high power applications come into play. The advantage of a hybrid system is, of course, the unlimited range. The range extension can always be done by liquid fuels such as diesel, H2, LNG, whatever. So there is no limit in range, but there is of course a lot of potential of using, for example, diesel fuel much more efficient. If you level the load production of a diesel generator system, for example, and you level all the fluctuations by a battery system, you can run the diesel system much more efficient. So depending on the type of ship and the load changes and fluctuations, it can be up to 30% of reduction of diesel fuel, but just adding a battery, which does all the work of taking energy if there is too much and boosting energy if there is not enough. And the diesel runs smoothly at the same sweet spot always. You've got of course, a lot of freedom of design. There is new and more efficient ship designs possible. Savings already mentioned. Fuel generations power, you may even can reduce the total size of the classical propulsion system. Maintenance is something which can be reduced because the runtime of the diesel generator system can be reduced. I give an example of a ship which has several generator systems on board, depending. They are used running at normal load, or particular parts are not running at all. So the overall runtime of diesel generator systems, if there are more on board, can even be reduced, which also reduces the maintenance cost. You also have an option to, at least part-time, sail fully electric. This can be, or is quite useful if we look into various ports in the world where electric sailing is a must. If you want to enter the port or want to leave the port, you have to do this electrically. Norway is also thinking of having regulations and restrictions of going to the fjords only electrically. So with a hybrid system, you can do both. You can sail partly electric for a certain amount of time, and when you're at sea again, you can do it in the classical hybrid way, so without any limited range limitations. And the big advantage is as well, you can use the existing infrastructure. So you may need, or you have an option for plug-in hybridization, so for plug-in systems, but in principle, the energy can be stored in the classical way. So you don't need necessarily for these kind of ships an electric infrastructure at the port. If it's there, it's fine. If not, it works as well. And of course, the main effect is that you reduce significantly CO2, you reduce noise. Think of electric port cruising, and NOx and everything around particle matter, which comes from an inefficient way of using diesel generators. So as an example, what we did, our aim was not just developing the same battery logic and the same battery system as always available. One speciality is that we're using LFP. So this is something which is not really new, but it's something which is not commonly used. And what we wanted to do is that we have a very flexible mechanical approach, that the battery will kind of fit also in existing ships and ship types, rather than forcing the ship to be entirely redesigned because a classical rack doesn't fit. So our aim was that easy marine should be easy to handle, easy to operate, and particularly easy to maintain. So the whole system consists of these battery cubes, which are combined to battery systems by combining them in a way the space requires on ship. Like, here is some configuration examples. So I think a nice description is of saying that this is like a Lego system for adults. You just put it together as you like. This system is easy to fit into existing structure of a ship, especially if you have not necessarily new builds of ships, but retrofits. It is easy to operate and also easy to maintain. You can access all parts from the front, so there is no need of complicated maintenance work. So things are kept as easy as possible. What you see here as an example, the red part is naturally it's not red, it's also white, of course. But this particular part hosts the BMS. So what we do is we build strings of battery modules to apply a certain system voltage. And each string has a master BMS, which has the same format as the modules. So it can be also integrated into the mechanical structure. Yeah. What's needed to get this on board a ship? So the first, of course, most important thing is the DNV-GL or DNV certification, how it's called today. UN 38.8.3, that's the transport certification. And what I also mention here is two particular norms out of the ESTRIN norms in Europe. And this is important if you go on inland water vessels. So we also certified the system according to these two relevant norms for inland waterways. So how is the electrical design organized? So as in every battery system, you generate a certain amount of modules that you put in series to get the system voltage. And the size of the battery you organize by putting these all in parallel. So that's like a matrix structure. So the big difference in Easy Marine, though, is that mechanically, this electrical design is completely disconnected from the electrical topology. So you can spread the parts where there is space at the ship, and just by doing the right cabling, you generate this electrical topology. Maybe some comments on the capabilities of the modules. The battery system voltage on a system level is currently limited to 1000 volts. However, the modules itself are prepared for string length up to 1500 volts. So whenever there's a need for higher voltages on a ship, and there seems to be a trend for that, the battery system, at least the modules, are prepared. The only thing we would need to do is to redesign the BMS to meet the higher voltage requirements. We decided not to do this in the first place, firstly because most of the ships have system voltages below 1000 volts. And secondly, if you go up to 1500 volts, you immediately raise cost on the BMS side significantly. So it makes sense to at least have various BMS versions available for different voltage levels. So in terms of power performance on module level, on cell level, it's much more on module level. We have discharge rates of 5C maximum and 3C charging rates continuously. We're not talking about peak power. Peak power is much higher, but on a continuous base, we can discharge with 5C and we can charge with 3C. So this is definitely best in class in the industry. So maybe some comments or information here why we use LFP. LFP is, as mentioned, not only a very safe technology, so it simply doesn't burn. So if there should be a thermal runaway event in the battery, there is no fire involved. So we could prove that in different and various tests, it simply doesn't burn. Next to the safety aspect, there is also a big advantage in terms of lifetime. So if we do full cycles, and full cycles at LFP means really from 0 to 100 SOC, we can achieve about 5,000 cycles. A typical NMC system, which is normally used, has limits at roughly 2,000 full cycles, if we really do the full cycles. So we have an extended lifetime. Therefore, as a consequence, we have an improved total cost of ownership, even if the systems initially are a little bit more expensive. Over lifetime, the amortization is, of course, much better, and it reduces a risk of failure because the system is very safe. Yeah? Next to that, there is also an effect which is also worth to mention there, but that's physics or chemistry. That the higher the average temperature of the battery is, the more the lifetime of the battery goes down. And as a rule of thumb, if you have something like 10 degrees in average higher temperature in the battery, that reduces the lifetime, and this is more like calendar life, by 50%. So it's very important to really make sure that your system has a very stable temperature regime. That's why we did two things. One thing is, of course, using high power cells enables or reduces the heat which is generated within the cell on one side. And we apply a liquid cooling system to ensure that the temperature regime within the battery modules is pretty stable and reduce the average temperature over lifetime significantly. This combination allows high rates for continuous charge and discharge. If you would do that with a high battery, with a high energy system, it will really heats up significantly. It allows the operation independent of the ambient temperature. So we don't need, let's say, AC for cooling the air that's used to cool the system. We just use water. In most of the areas in the world, we can simply use the water which is available outside. The temperature is low enough to have a cooling path, which also improves the TCO and, of course, reduces risk of failure. So there's also a reason why we choose to go for a liquid cooling system. So how is a ship battery usually developed? So the entire chain starts from the material. So that's what we buy. We make the cells according to the needs of the application and the system. We build the modules, we build the battery layout, and we do part of the system integration. So basically the right part from material to battery layout is something which we cover fully within ES batteries. And that's unusual because most of our competition, if not all, are using cells supplied from Asia. So they're not doing their own cells, they just do the systems. So we have the full chain under control. If there is a need to adapt the cell, we can do that. If there is a need to keep the cell available for 20 years, we can do this as well. So we're not depending on any supplier on cells. If they do any change, we have to adapt. We can still keep what we intend to do. On system integration, things come together from the left side, from the application requirements, which leads into a set of system requirements and a system layout. And the system integration finally is the critical part where all things come together in applying and integrating a battery within a hybrid system or propulsion system, whatever. Yeah, and this is something which we do with partners, and we are also always looking into new partnerships, make sure that partners understand how our systems are working, how such a flexible system can be integrated in a ship from a mechanical and electrical viewpoint. Okay, finally, why Easy Marine? So it has the highest power in class. Where there is a need, if there's a need for high power ratings, as mentioned, see peak, it's a perfect choice. It has the lowest price per kilowatt. So if you're looking for power performance, this system comes with a pretty efficient and economic number. It's the most flexible architecture in the market. So it's fixed and there are no racks needed. So if you have limited height or even decks, intermediate decks, you can fill them with a battery system because you don't need a rack. You're not limited to certain minimum sizes. You're just flexible. It's a very safe and reliable chemistry. So there's no fire, no propagation, and highly enduring cells. And EAS batteries as a company is highly vertically integrated. So we start from cell block battery system. It's basically a one-stop shop. So as saying that, I just want to go a little bit back in our history. So we started to do marine battery cells already in the past. These were all individually generated and developed cells. So this is not based on Easy Marine. This is something we did individually for particular applications. This is an example for a live example of Easy Marine. That's what we showed in the fair in Amsterdam. So this gives you a glimpse how the system looks. Of course, in practice, there will be cover lids in front of it to protect the cables and the system. What you see here as well is that everything is available from the front side. So if there is some issue and you need to change a module, the inside of the module can be easily pulled out it's like a drawer system and can be replaced with something else. So it's pretty easy. Yeah, there is also some references around a military application and leisure boats. One example is TKMS. That's a German manufacturer and producer of submarines. And for leisure, these are these kind of small submersibles where we supply also the battery packs, the cells. And this is probably one of the most famous ships. This is a solar boat, which is fully staffed with our batteries and our cells. It has latest been changed to a hybrid system, including hydrogen. So they also produce hydrogen now with the excess energy of the solar cells, but still buffered with batteries that come from EAS. Okay, for those who are maybe a bit more interested in the technology, this is an example how a hybrid system can look like, for example, at a river cruising ship. That's an example of a river cruising ship. So here in this case, you've got 1, 2, 3 large diesel generators and a smaller one as a backup, combined with battery systems. So there's a certain redundancy in the system, but this would go too much into detail. I don't want to do that now. But what's interesting here is they used to have 4 diesel generators driving and running the ship. They were never in their sweet spot. They were just running and they had fluctuating loads. So by applying a battery, it is usually the case that at least one diesel generator can be switched off entirely, where the other 2 are running on full load. If the battery is full, you can switch off one. If the battery is empty, you start adding another diesel generator in its sweet spot and just supply the energy need, and everything which is in excess, you add to the battery. Once it is full, then you switch it off. That's what I mentioned in the beginning. then you can even reduce the runtime of diesel generators, because not all three are running, or even four in the past, are running permanently. But in most of the time, it's only one or even only two running at the same time. Just if there is need for more, you just add the third one or you to recharge the battery. But it gives an example how hybridization could work even in complex ships with a lot of driving electrical motors that drive propellers for maneuvering, for thruster systems, and so on and so forth, and also for the supply of the electric systems on board, like the kitchen and all the stuff around the cruising ship. Okay, so coming to the end, what I'd like you to take home actually is the lithium-ion battery technology is kind of a revolution. Everything becomes electric. That's the long-term view. There is no new storage technology in sight that could outcompete lithium-ion in the near future. Even if you read some nice developments on lab level, for the time being, lithium-ion will be the main let's say widespread battery technology for quite some time. There are multi-billion euro markets beyond automotive, even often with a much better return on investment. Automotive cell designs and cell specification are in general not suitable for industrial application. And I give you an example here, which is linked to the cycle life. If you think of a car having a reach of 300 kilometers, then 1,000 cycle would mean 300,000 kilometers of range in total over lifetime. I think for most of us, we agree that this is more than sufficient at a car. This simply means 1,000 cycles is enough for a car, but it will never be enough for a ship. If a ship is in permanent service, you definitely need cells that go much further than just 1,000 or 1,500 cycles. So more cycle life means longer life of the battery on board, longer use, and therefore also a reduced total cost of ownership. Vertical integration from cell design and cell chemistry up to finally battery is highly advantageous. So as mentioned, if you have the cell design and the cell performance and characteristics under control by doing this yourself, you first do not depend on suppliers that can change their recipes just as they like, because they're probably focusing on other markets than you. So keeping that knowledge in-house is a huge advantage to build systems that are more suited to the particular application. There is significant potential for improving production technology and product design. So that's what we're going to do. You may remember that I mentioned that we have also a 50 amp hour cell already in the portfolio. And the next step, we use this cell and put it into the Easy Marine system, which then leads to a medium power solution, which can address further applications in the ship, but still focusing on hybrid systems mainly. Yeah? Lithium-ion technology is complex and needs a broad array of know-how and competencies in terms of chemical, mechanical, electric, thermal, digital, production, market understanding, etc. And that's where we see, where I see ES with particular strengths, because we're really coming from cell to system. Okay, thank you very much. I'm looking forward now to some questions. Hope you enjoyed it, and thanks for listening.
Yeah, thank you, Frank. Is there any questions from the audience, please? So till somebody is still thinking, maybe I have one question. It's more for me interesting. We are now busy about some small autonomous devices, and as far as I understand, then your model is having 38 volt power, but when I would like to have a bit lower, then is that possible, the custom made? Because you were mentioning that you were making some custom made things previously. Is that possible to have smaller voltage modules?
In principle, it's possible, yeah. So just to give you an idea, in the module, we put 24 cells. And it's a 2P12S configuration. So this means we put 2 cells in parallel and 12 of these pairs in series. That's why it comes up to 38.4 volts. Mm-hmm. If you want to have a lower voltage, there is an option of doing this with 3P8S. It's the same number of cells, so we would not even have to change the number of cells in the module. Then you could come down with the voltage. That's possible. We haven't done that yet. The point is, once you want to put this on a seagoing vessel, you have to undergo the full DNV certification. So before doing that, you have to always consider the cost involved. If it's something which has to be done only for a particular project, yes, certification costs come on top. Yeah, it's not now. It's not a standard product in terms of we did the job and then you can just benefit from what we've done. But it is possible. Technically, it's absolutely no problem.
In my case, I believe the certification will be not so very important, at least in the first stage. But okay, thank you.
So with some adaptation work, some engineering, the BMS has to be adapted as well. But at least one thing is clear: you don't need to undergo the complex and costly certification process. Yeah, mm-hmm. It's possible. Yeah.
There. Any more questions to Frank? So, when there are
late. Oh, sorry for that.
Yes, okay. That's I believe. We will maybe gain it a bit later, but thank you, Frank. So the next presentation, Daniel is back, I see, and hope there will be no problems anymore. Then please, Daniel, take over.
Well, thank you very much. Can everybody hear me?
Yes.
Yes, that's good. First of all, my apologies for the problem here, but I'm joining you from my vacation hotel, and the problem is that the bandwidth here is not optimum. And also there seems to be some limitation of the network system that can cause some issues. So let me share the screen with you. And then we can go full steam. Some of you already know me from the past, where I was actually part of this group for the company IPT, but I'm not with the company IPT anymore. I am presently working as a consultant in this whole field, and so that's why the layout changed and everything. And I'm not going to go specifically into one company technology. I'm giving you an overview of what is possible, and there are numerous companies active in this field, and we can talk about that later. So it's about the wireless technology in this case for electric vehicles. What you see here as an example is the Fredrikstad City Ferry in Norway that has been fully electrified by the company IPT, but I'll come to that in a little bit. First of all, about myself. I'm in the industry of electrification for more than 25 years. I've been CEO of numerous companies in the industry, but also for the car industry, this technology, wireless technology, is an interesting thing. And we've realized a lot of projects in various applications over the years. Typical examples are, well, you can find it in forklift trucks, cars and vans, where power requirements are rather low, where charging of the battery happens in areas of, let's say, 1 to 20 kilowatt of power transfer, which is rather on the low end. But there are also companies in the market that have specialized into higher power, and you find applications for buses and trucks like London, Madrid, and other parts of the world where I've been involved, but also ferries like the one in Fredrikstad that was realized with the company Swedship. Yeah. First of all, about the wireless technology. The wireless technology is a rather old technology. In the 90s, numerous pioneer companies developed the first wireless power transfer systems. Some of them we can name is the company Vale that worked together with the University of Braunschweig to develop systems, but also the company Wampler AG that had a cooperation with the University of Auckland. Yeah. That happened in the early and mid 1990s. From 2007, there was a big movement that wireless technology could also become a very interesting technology for the car market and for the whole e-mobility movement that was starting to become very popular. And that's why a lot of other companies became involved. Some of them are Kaist Olef, state-owned company in South Korea. Bombardier acquired a lot of patents and became active in Canada, mainly for tramway system, as you can see it down here. There were some industrial companies like SEW Eurodrive in Germany. There were companies like Intis Germany. They were a spin-off of the magnet trains that Siemens developed. The magnet trains that Siemens developed also needed data communication and low power supply. And the technology developed there was also then used by Intis for other applications. There is the company Delta in Taiwan nowadays that is very active in this field. There is a company Witricity in the USA that has collected nowadays more than 1,500 patents around this technology and is trying to promote it. And there's a company Momentum Dynamics that is also mainly active in the high power field. So you can see in the meantime, the landscape has changed dramatically, and then nowadays a lot of companies are active in this field. The technology of wireless transfer power is a very simple principle that goes back to the development and the research that Nikola Tesla did more than 200 years ago. So the main principle is very difficult to patent, but a lot of things around the technology are patented nowadays. Due to these new developments in the 90s and 2000s, it all of a sudden became also an interesting technology for industrial applications, because semiconductor technology became capable of switching high currents with very low losses. And this was key to really establish technologies in this field that are economically interesting. Yeah. A typical example is this QI standard. Nowadays, all mobile phones can be charged inductively. Of course, this is only 5 watts of power, but it shows the potential of the technology once it's rolled out in a high volume scale. What we also see is that the fast developing electric vehicle market gave this technology a very strong boost in the mid 2000s down to the last days. And I think this will be continuing. There are also nowadays already several standards for the wireless power technology. As you see it here in the example, there is this QI standard for wireless charging of mobile phones, but you can also find the first standards for medium power transfer, which is this SAE J2954 and the IEC 61980 for the car charging between 3 and 11 kilowatt. This makes sure that all the companies produce at the same standard, and a vehicle and a charging station are interoperable even with different suppliers of systems. And there is also movement for higher power applications for standardization. So this will come in the next years, and I expect that by the year 2025, there is also going to be a standard for high power transfer beyond 50 kilowatts and significantly higher. How does a wireless system look like for charging of electric boats and ships? Well, you always have to distinguish two parts of the system. One part is everything that goes onto the ship or the boat, and the shore assembly. The two systems also have to be designed to completely different standards. So it's a bit of a tricky situation and a tricky thing for the companies. They have to be capable of dealing with both worlds here. You typically have on the ship a pickup, which is usually a coil picking up the electromagnetic field generated on the primary side. And this coil generates a high frequency current that is led into through the wiring inside of the ship to a rectifier. And this rectifier transfers the power from a high frequency AC to DC. That is compatible with the charging voltage that the battery pack requires. So it can be designed in different types. Typically nowadays, you find battery packs mainly coming from the car market in the range of 300 to 400 volt voltage, or up to 800 volt when it goes to more high power applications, and especially in ships. I presume that high power applications will be more predominant, and that's why this is probably going to go to higher voltages. Just like Frank mentioned, it will stay below the 1000 volt level probably, and that's mainly because of standardization and homologization. But a higher voltage requires lower cross sections in cabling, and this is saving costs in the end if you can comply with the voltage standards. And then on top of that, you need on the vehicle then also some kind of communication unit. The communication unit, first of all, talks to the main control of the vessel or the ship or the boat, and it's also responsible for the communication with the shore unit, and the shore unit needs to understand what the vessel requires. So typically what you find on the shore side is the corresponding coil that produces the electromagnetic field that is being picked up by the secondary coil here. You need a tuning converter, as we call it, that changes the DC from the shore unit to the high frequency AC. And of course, you need the whole cabling, and you need a shore unit that picks up the power from your grid and transfers it down to a DC. So a wireless system always transfers the typical 50-60 hertz AC power from the electric power from the grid to a DC power in the first stage, and then it converts back to a high frequency AC. The whole system needs to communicate between the vessel and the shore assembly system, mainly because you always want to make sure that you only generate the power on the shore side that is really needed by the vehicle. So the state of charge of the battery defines the power requirements of the ship, and once that is determined, the shore assembly automatically generates this power level that is required to recharge the battery in the most efficient and fastest possible way. Yeah. For maritime applications, high power applications above this 11 kilowatt, there are very few companies that have realized systems so far. One of them is the company IPT Technology that I worked for. It's a spin-off of Conductix Wampler, and they can realize systems that can transfer up to 200 kilowatt of power. And one good example is this Fredrikstad ferry in Norway that is operational since 2019. So it's not a prototype system. It's really a system that is in everyday use. The second application that we find, the company Wärtsilä producing ships in Norway, has tested a wireless charging system at a hybrid coastal ferry, a much bigger vessel, in August, September 2017. I think this system is not operational anymore. It was only installed for showing the possibilities of such a system. They claim that up to 1 megawatt of power transfer is possible, but I believe this is to some extent questionable because it would require a very, very heavy system. And it's also in all cases important that the higher your power transfer is, the more complicated it will be to control the electromagnetic field. And the electromagnetic field needs to be controlled in order to make it safe, because electromagnetic fields, there are standards of limit electromagnetic fields, especially when humans are exposed to electromagnetic fields. So you have to be very knowledgeable about electromagnetic field design if you manufacture systems like these. The efficiency of these systems, and that's a bit just a theoretical thing, is because you have one more transfer stage compared to a plug-in system. A plug-in system typically transfers your AC off the grid with 50-60 hertz to a DC power, and then you plug it into your system on the ship or vessel. If you do that, you typically can reach efficiency levels of 94-95%. If you do it wirelessly, then you have one more transfer stage, and this transfer stage adds a few losses theoretically, which is typically in the range of 1 to 2%. So you can see a wireless system with looking at all the other losses around the system in general, offers really a good performance of typically beyond 92% overall efficiency compared to a plug-in system. So looking at the typical plug-in systems that are available on the market, the difference is really neglectable nowadays. The power levels go up to 200 kilowatts, but in the future, there is developments by various companies in this field to increase the density, the energy density of these systems and the power transfer levels. And one example, I know that there are companies active that use the same envelope and the same space, or that a 200 kilowatt system today requires to transfer up to 600, 800 kilowatts in the same size of system. And this will really open up new possibilities, especially also in the maritime field, where power requirements are typically higher. What are the advantages, especially in the maritime industry, for wireless systems? Here on this picture, you can see this Wärtsilä ferry with the wireless power transfer system. Down here, you can see the ferry in Fredrikstad. It's always a very similar concept. You have a primary pad and power electronics here, and some mechanical system that can is responsible for the vertical fluctuation of the ship due to tidal changes or waves. If you apply this system on a floating dock, then of course you can eliminate all those changes, because the ship and the floating dock have a similar movement, and the typical tolerances of a wireless system can be easily maintained in this scenario. The good thing is that you have no live open contact, because everything is completely enclosed. The electromagnetic field goes through air, and that means it's completely sealed. You have no risk of short circuit with water entering, and you have no corrosion whatsoever. That's a really big advantage of a wireless system in a maritime application. It is very safe, so you can even, I know that the development engineers have no problem touching it while it's active, etc., because if you do that only for a very short period of time, it's not a problem. And you have no cable handling, no cables laying around at shore side, with the risk of people stumbling over it or accidents. And the electromagnetic fields can be limited through professional design and the shielding of the system to the levels acceptable to human exposure. So that is really not a significant problem if it's designed professionally. It can easily be automated. So compared to a plug-in system where you need people plugging in, there is no manual plugging necessary or no complex robotic plugging necessary, which is saving significantly on labor cost. This was one of the reasons why the ferry in Norway was equipped with this system, because normally if they would have to do it with a plug-in system, they wouldn't have to tie the vessel to the dock while people are entering and leaving the ferry. With this system, they don't need to tow the boat at all. It's just held in place with the normal motors that the ferry uses for the thrust. And the wireless system can handle the tolerances very easily. So in summary, it's ideal for ferries or other ships that always stop at defined points. One of the reasons why wireless charging has not spread out very, very strong is the missing standardization, especially for higher power. So if you have a ferry operation like this that operates always at the same points, and the shore side and the vehicles are owned by the same company, then it's rather easy to adapt in this closed system. And if the distance is to be covered between one side of the river and the other, or an island and land is not too long, then battery-driven vehicles can be used, and the high power demand can be easily handled by regular charging. And with the high powers that can be provided through these systems, typically that is not a problem. What we see in most of the applications is that with 10 minutes of charging, you can run the system for about 1 hour. For a typical passenger ferry like this is more than enough, because the transfer time from one stopping point to the next is usually significantly less than an hour in these applications. And the waiting time at one point is typically 15 to 20 minutes for the people to board and leave the ship. What is the typical project timeline that you need for realizing such a system? Typically what you see, you need to do a very thorough analysis of the application to really make sure that the power requirements are clearly defined, and the battery sizing can be done thoroughly. And then you can define the charging power and the location of the chargers. There's a lot of variables around that, and to find an optimum solution not only relates to the ship size, the battery size, the charging power and the locations, but also the availability of power from the grid side, etc. And all of that needs to be combined, and that usually takes about 3 months. And then you need to do a lot of detailed engineering and integration planning for the boat or ship side. That typically takes roughly 6 months. And you need to do engineering and planning also for the shore side, including the grid connection, which usually is a bit quicker because the limitations in space are less tricky, and that's why around 3 months is fine, should be fine. And then you have to build the components and deliver them depending on the partner you select. This is a typical 5 months period. Once this product is standardized and is used, the delivery times go significantly down. And then preparation of the boat and integrating it into the boat, when you do it the first time, takes a little bit longer. Our experience is something like 6 months. And then you need to do testing and homologation of the overall system. This is typically done by the shipbuilder, which takes another 3 months. So for a first solution, from the first discussions to really realizing it, the typical time frame that I see is between 1.5 and 2 years. Once this is established in the ship, then of course, for second, third, and following solutions, the delivery time goes down to 3 to 6 months. So just as a rule of thumb, if you really have the idea of doing something like this can be a good help to understand the time frame that is needed. So in summary, this is a bit what can be done with wireless charging. And if you have any questions, I'm happy to answer them. And we as ETAC are always happy to realize systems like that with any interested party. We are neutral in this field. We can also realize conductive systems, but my specialty from my background is the wireless technology. So thank you very much for your attention. And if you have any questions, please feel free to ask them now. Yeah.
Thank you, Daniel. Is anybody having questions on the wireless technology for the ships? At least I will have the question. I'm coming back to my topic about autonomous small devices. And here for me, it is interesting yeah, of course, there are also chargers for telephone, but in this application, what is the smallest size you can provide? Is there that technological limitations for the scaling down?
No, there is no limitations for scaling down. The problem is always what power levels do you need to transfer in kilowatts? Because at the end, your coil inside of a system determines the size that is relevant for the ship or the boat, and the coil size depends on the kilowatt that you want to transfer, and it depends on the positioning tolerance that you can achieve. Once you have a very small coil, positioning tolerances of 5 to 10 centimeters can become an issue, because the overlap of the electromagnetic fields really determine how much power you can transfer. And the smaller your device, the bigger your change in percentage of overlap once you misplace. And that's one of the key elements that you have to consider. But for example, I know of a 1 kilowatt system which could be used for a small autonomous vehicle on water. I know, for example, that for exploration of or measurements of temperature, water quality, etc., you have these small robot water vehicles that can be charged easily with 1 kilowatt, for example, with the size of a 10 centimeters in diameter of a coil. Yeah, that is not a problem at all. And you also see that the development is going towards smaller systems with higher power density in the future. This is mainly related to new power electronic switching semiconductors with gallium nitride and silicon carbide technology that is available now, which will reduce the size again, because you can transfer the power with higher frequency electromagnetic fields. And the higher your frequency of the electromagnetic field, the better, the smaller your current inside the coil. And the current inside the coil determines the cross section of the wires that you have to use. Yeah.
Mm-hmm. Okay. Thank you. And just also when you were speaking about the ferry in Friedrichstadt, but you already said that it is taking around 10 minutes to charge it, that it is running with the battery capacity for the optimal operation. But then it's just to supplement, I believe, the presentation we can after put on the ELMAR webpage, and there could be a link. I know there is a good video about this ferry.
Yes, there is a video about the ferry where you see everything. I added the link to the YouTube channel, but I did not want to stress my bandwidth here in the hotel. Yes. So please have a look at that video. It shows a nice example of this Friedrichstadt ferry, and it also gives some more detailed insight. And it really works quite well, I believe. Yeah.
Further to say, I will send to everybody after the link to the information that we are recording today, and the presentations also. Then everybody can look once more. Okay.
Well, thank you very much for your time. Once again, Vasily, I'm not sure whether my bandwidth will leave me again soon. So. I probably will not be around for too long anymore, but if you have questions, Vasily, you have my contact details, yes, and you can send them around as well. So if there is any question, please feel free to contact me anytime. Okay?
Yes. Thank you very much, Daniel.
Thank you very much as well. Bye-bye.
Okay, bye. So we are continuing, and next in our presentation is company Euronavis. Dino, please, the floor is yours.
Okay, thanks. Hello to everyone, and greetings from Croatia and from one small company that trying to join this current developments and new technologies. I'll try to share my screen. Do you see everybody?
Yes, we see it very well.
So, Euronavis is a company founded by naval architect, me, who have 25 years of experience in other companies and various types of ship design and building projects, and well-developed connection within Croatian ship and yacht building industry, which could be also a valuable asset, of course, for professional networking. Our desire is to invest knowledge and years of experience in the field of both shipbuilding and related marine industry to provide the services required by boat and shipbuilders and boat owners. In line with that, we aim to provide a quality and professional service that can only be expected from high qualified and trained employees who are able to approach tasks or projects consensuously and responsibly. Since we are constantly monitoring the market and trends in the world and in this industry, through our offer to our customers, we want to ensure the availability of the latest and most advanced technologies and products. Our references include different ship design projects, boats, yachts, fishing vessels, ferry boats, patrol, coast guard, etc. Regarding all above mentioned, we have possibility to offer components or complete system consisting of engine, outboard or inboard, lithium batteries, chargers, battery management systems, and knowledge to design and integrate electropropulsion systems for all types of boats and ships. Our technical team is ready to assist in custom-sized projects or to offer solutions for electric propulsion projects. Together with customer, we can look for the best solution, taking into account the requirement of product, suitable technology, dimensions and weight, shape of the required motor and battery. In cooperation with our partners, we can carry our scientific and technological research and investigations into new laws regulating watercraft in EU, as well as offering advice on design and construction techniques, prepared documentation, planning general and special maintenance procedures, checking quotes and performing test trials and certification. Modern shipbuilding is characterized by high degree of integration. A number of companies from different countries take part in the development of one ship project. In line with this, it's helpful and a great asset to have good connections with many companies and colleagues, experts of various fields. Regarding that, I would like to express my gratitude to the invitation on this event and looking forward for any potential cooperation. Now something about companies that we represent in Croatia. Enave is an Italian engineering company and a notified body for recreational crafts and deals with issuance, renewal and validation of safety certificates and other tests required by international regulations about EC recreational crafts, both power and sailing, monohull and multi-hull, and personal watercraft according to the Recreational Craft Directive. Whilst Ridley is from UK, marine hydraulic steering gear, electrical controls, or other technical procurement specialist. There is also in NASA, one of leading European suppliers of spare parts and marine equipment for professional users, nautical sector, services, marinos, charter companies, etc., and is ranked within the first 4 companies in the sector in Europe. They can cover and supply equipment and spare parts for all ship systems, electrical power systems, ship propellers, shafts, deck equipment, etc. Carvin is Czech Republic manufacturer of electric motors and batteries from one smaller manufacturer. They have few types of outboard motors and pod versions, equivalent 16 horsepower or 24, and batteries or supply batteries for those engines, lithium and NMC, and chargers. Also, we're starting to cooperate with Edin Marine innovative solutions of electrical propulsion technique in field of nautics from Slovenia, enabling people all over the world to enjoy pure and more environmentally friendly water mobility. And Sandware, German producer of solar systems and panels. Edin has wider panel of products, outboard engines from smaller 2.8 kilowatts to 20 kilowatts, pod versions for sailboats are similar from 1.6 kilowatts to 10 kilowatts, and classical inboard engines for larger boats up to 150 kilowatts. And of course, they supply also batteries and whole systems for boat retrofitting. And this is some example of Sandware solar panels, which are high quality, possibly for gluing and screwing, and on the decks, superstructure. And that's all. And thank you for listening me, and I'm here for questions. This was one short presentation.
Yeah, thank you, Dina. I have the question: is there maybe some if you could provide some examples of installation of such systems, or I believe there is the experience behind for, let's say, Edin looks for me very interesting, even till 150 kilowatt engines. Some where it is installed.
They are also just started. You can see on the website, and they on the YouTube. They produced just one power boat, and recently they participate in Monaco boat show on some race of electrical boats.
So we should go to Monaco.
Yes. And in Venice before that, Venice boat show also. They actually just started to promote broadly their products and services.
So, as I understand it,
I didn't see yet some installation of that bigger engine somewhere.
Okay, so I understand it is a young company, generally. Okay. Do we have, do our audience have questions to Dino? I see there is no more questions. Thank you, Dina. I will maybe say one more time, but then all the materials I will after the supply to all participants, and you can find the presentations and the contacts also on the webpage. And if there will be more interest, you can also find the contacts in the agenda. Either you can contact me directly and I will make forward. We are even good on the schedule. Now is by the our agenda is a small coffee break, and I believe we can. Yes, come back now in 25 minutes as scheduled, and we will continue on with the Western Baltic Engineering. They will speak about the ship design and the designs that they have in stock related to electrification and hybridization, and also followed by green boats who will share the experience of the building pure electric boat. And even last week it was there was a demo trip, and they will share some experience how it came within the result.
Yeah, can you see it?
Yes.
Okay, so our Western Baltic Engineering company presentation for ELMAR online dialogue event. So I want to begin with our picture at glance, what we are. So basically, we are a company which belongs to Western Shipyard Group, and this group belongs to BLRT Group. So we are total for more than 3,000 workers in this group. We, as Western Baltic Engineering, was established in 2003, and now here is working around 100 employees. Our services, as you already mentioned, we can offer retrofit and conversion projects. So it's included ballast water treatment system, project management, and technical support, and of course, new build design vessels, and concept and full project development. We are mainly focused on fishing vessel, general cargo vessels, service vessel, and it's including bunkering vessels, barge, also inland water vessels and offshores. Our past 5 years, our key points. So basically we have made more than 12 concept designs, working, as already told, 100 engineers, and made some conversions and fishing and aquaculture vessels. We as a design company can offer from A to Z. As already mentioned, as we belong to the shipyard group, so we can offer also in workshop documentation and production, as we have our own experience in the shipyard building and repair. This is our tools. Our engineers are mainly working. This is one of the most popular. And now let's talk about services and support. So as you can see, we have made and designed tugboats, dredgers, inland water vessels, as well as research vessels and barge. This is our mainly focuses on passenger vessels and ferries. As you can see on the right corner, this is our newest Klaipeda ferry for the Smiltynės Perkėla. And here's aquaculture experience. As you know, our Baltic region is highly involved in the fishing area. So of course we are making design and engineering for fishing trawlers. One of our key points where we are looking forward as a company, it's LNG bunkering vessels. As we can see from the demand of and building in the LNG vessels in the Asia, in the Europe, we can see that the bunkering will be highly needed in the upcoming years. So, and also in our Baltic region. So we have made two concept design for 1,000 cubic meters LNG bunkering vessel and 5,000 cubic meters bunkering vessel. Of course, it can vary and dimension can be changed and implement for the client purpose. And now let's talk about our research and development activities about autonomous electric ferry, which we developed together with our great partner Klaipeda University, and which is funded by operational program for the European Union funds, investment in Lithuania. So main particular of this vessel is, as you can see, length around 35 meters, and it can carries 300 passenger and 40 bicycle. Its preliminary speed 8 knots, and it's basically for our Baltic region, for Lithuania. Project scope. So this project is for innovative health form for electric passenger ferry development. We want that it will be development and optimization of electric propulsion complex, and it will be for autonomous ferry. Autonomous system has to be integrated into ferry, and it has to be autonomous system maneuvering, testing, and prototype. So about these various systems. So voice control system, it has to be included navigation console and control from shore system. Follow-up is electric engine system data and BMS data, navigation system, and propeller data. Artificial intelligence is autonomous movement and maneuvering, and also autonomous mooring system. Cybersecurity system, of course, as an energy system. So it's really sad that our project manager is on the holiday, because as per previous presentation, I believe that she will contact our colleagues about batteries and all other systems, because it's highly needed right now, because we are thinking about how and when we can install the system. So I think later on she will contact. And also, if we return to the presentation, so propulsion system, electric engine, and navigation system. So that will be shortly for autonomous ferry systems. And for the end, let's design future ships together. So it will be shortly for Western Baltic engineering.
Okay, Jonas, thank you. As far as I understand, you are still in the search of the components for the electric ferry.
Yes, because it's still under negotiation how the batteries can be charged, because there is a short between Klaipeda and Peninsula, so it's short range for standing in the quay. So this is the main, not a problem, but the good question for our engineers.
Yes, when we take in consideration our ferries, the operation regimes, then generally they stay by the quay around 10 minutes, I believe.
Yes.
And when you also spend time for connecting, this time comes really really small time to charge, means either you should charge once in an hour or once in a few hours, or there is another possibility that Daniel was presenting.
Yes.
That you are charging with each time coming to the pier and topping up the level of the batteries to the necessary operational range.
Yes.
That could be a very nice solution for this ferry. Okay, thank you. And if somebody would like to ask something, or Jonas. Okay, then when there is no more questions, Jonas, I thank you, and
Thank you.
I hope this event will be also very efficient for you, and you will find also more possibilities to charge and to have some batteries. And next and will be today for today the last is the presentation of green boats. Evaldas Narušis will present the result of the ELMAR project demo boat that have been done during this 4 years that project was running. Please, Evaldas.
Hello, everyone. Okay, I'll share my screen. Okay. 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 Everyone is. Do you see my screen?
Yes, we do, Evelyn.
Okay.
Yeah.
So let me present you our project and its results. So something like 5 years ago, we bought some old rescue boat. It was in very poor condition, the hull, and we decide to retrofit it to electric 12-passenger boat. Okay, and some short overview of our electric design of electric components. So we took small brushless motor. It says it's up to 30 kilowatts, but we didn't test it yet. But currently we know that our vessel is quite happy with 10 kilowatts of power. Yeah. So, but it can be even forced up to 30 kilowatts, but we don't need that power. We built the battery from the Tesla battery modules. In total, now theoretically it's 60 kilowatt hour of power, and the charging capacity is only charger is limiting us. We have 3.3 kilowatts of charging power. It takes about 16 hours to charge fully our battery. And there's some custom-made battery management and automation systems. Okay, so very first steps was to do 3D scan of the hull. Here you can see the raw data. Then was modeled through that scanned points was the hull modeled with Delft chip software, and then on that model the all existing planes was designed, and later from that stage the design was started. So we designed a small cabin, the open deck with the steering wheel and console. Yeah. Okay, and simultaneously the whole renovation was started. It was in quite poor shape. So firstly we fixed the sides of the vessel because it was very cracked, and later we turned it keel towards the up, and did tiny renovations. The bottom of the hull was not in so really bad condition. We did many sanding. You can see some spots where we have the filler, and this is the hull. So it means that it was not really straight and nice from its fabric, because a rescue boat doesn't need to be very nice and really. Yeah, here you can see the big areas of filler covered. Yeah, and here you can see the cracks. All that cracks it's not the biggest ones, but all that cracks is fixed. The poor condition glass fiber was removed and covered with new one. After that, we cover it with primer and then with anti-fouling, and then we took back in normal position and continued to fix the sides and the edge and the sides. It took very long time, and we spent many man hours to do this. Next steps was to work with interior and exterior. Here we cleaned and filled it with filler. There was some cracks also inside because the hull was on an open area left all the time, and it was full with water, so everywhere was cracks. And so we fixed that and then started to install wooden constructions, supports for cabin, for seats, for some space for storage. Everything is sealed and covered with epoxy resins, and so to make it durable for moisture and the water. Yeah, it's the bottom, preparing for the bottom. There is some image of deck. Inside deck there's only preparing. This is some nice and easy technology how to make the contour of existing part, and after you can cut very nicely. The outside works. There was many challenges because of the water, how to make the water go not inside the vessel as usual for that kind of vessels, but go direct outside. Yeah, here you can see the propeller shaft installation. There was also some challenge. This is the truss bearing installed, and we need to make some link angle here because the propeller shaft is straight and the motor won't fit there. So we installed some angle joint for the shaft. Yeah, here you still can see the pictures of truss bearing installation. It was done very precisely to avoid any vibrations. Yeah, this is still the old propeller. Bilge pump. Yeah, still installation. This is the motor. We choose to use belt drive. It's silent and low maintenance. We are happy with it. Works very fine. The motor also, I think, has enough torque to spin the propeller, but we did some reduction because theoretically it should be more effective. Yeah, we still don't have very much of the data, not yet collected, but the results is happy. The results is good for us, and we will continue to test the system. And here you can see the results of our short test on the water. Here you can see that with 6 kilowatts, the vessel is sailing even faster than its regular cruising speed. So I think that 5 knots is the very good speed, and with that speed we use only 2 kilowatts of power. It's not much. And here you can see the estimation. It's only theoretical, not tested yet, but I think it can be something close to that. Yeah, the estimated range, it's still only theoretical calculations. Okay, thank you very much. Maybe there are some questions about our project.
Thank you, Evaldas. It's very nice to see the electric system in the vessel, and the ship has the second life. By the way, I've just was day before yesterday, I was in the boating area also, and I saw also a boat very similar to yours in the poor state, staying on the ground upside down. And I said, yeah, that's the second one. Really similar. But of course,
there is plenty of that kind of the tools.
Yes, but this 2 kilowatts that you say for the 5 knots, it's really very nice, because when you have a pleasure boat and you like to stay calm in somewhere on the water, enjoying the atmosphere, I believe that is quite good speed for such a purpose. And with the 2 kilowatts, you will have, I believe, the range quite that will be hours and hours. You can, I believe, a few days will be enough to to sail. But then even you said for the 16 kilowatt 60 kilowatt hours, you need 16 hours. That's from one side, it's for the each day, usage, even could be enough when you use the boat 8 hours a day, generally. Then it's of course it's on the limit, but still it's quite good characteristics. And from another side, when you do not need to charge it each day, that is also quite a good. So please, anybody has the questions to Evaldas, because they've gone really good way to from the scratch till the final results. And last week there were demo tests of the boat. Can you share a bit of experience, Evaldas, maybe? How do you find the result? Are you satisfied?
We still need to do longer trips, but there is something to check and to improve. We need to know more about the cooling. Now we are using passive cooling, so no cooling at all. So we are still deciding, do we need to water cool the motor or not? So the drive is cool enough and the motor seems to be a little hot, but it's not that hot that it's danger for the motor. Next thing, we need to maybe to adjust the power for the motor. Sometimes if we get some growth on a propeller, some seaweeds or something like that, we lose the power. But in current stage, we are limited the power of the motor. Yeah, so maybe I need to increase the power to, in case you have some marine growth on the propeller, you just increase the power for the propeller and they will be blown away. Yeah, and yeah, we need to improve the maneuverability for the vessel. It's quite tricky to turn around in a narrow channel. It's possible, but it's need good experience of the. Yeah, and still we need to do the one sailing from 100% of the battery to the 0. It's not done yet, and we'll see the final numbers, how it is.
Mm-hmm.
But for general cruising, and I think it's okay. I calculate like 1 hour of charging, 1 hour of sailing. If you have the right infrastructure, you can triple the charging speed. So it means 20 minutes of charging, 1 hour of sailing.
So generally, it's quite okay, and you have still then the possibility to upgrade the charging when it will be necessary.
Yes.
But then remembering what Frank said, that for the batteries, the higher the temperature of the batteries, the less the life of the batteries. Is that the case for you, or the batteries stay cool?
No, in our setup, batteries is cool, and because of that big amount of the battery that we have, so the batteries don't feel any
Heating.
Big power charging or discharging, so they feel very good.
Okay. But then you said the maneuverability, is that the case for the boat thruster?
I think for improve of the rudder.
Ah. Mhm.
I think we need to do it more balanced rudder, make it longer the part that goes towards the propeller, because now if we turn the steering wheel to one side, there's still some area of the propeller there that it's making forward thrust. So we need to
Cover that.
close that area
Yeah, close.
to as much as possible. So we took forward thrust and push it, make it to the side thrust. Usually that kind of vessels are quite steerable and maneuver enough without boat thruster.
Mhm, mhm, mhm.
And for the boat thruster, the draft it's not so big of that vessel, so I don't know.
Well, there are some small boat thrusters that would help, I believe. I don't know, Dino maybe have the something to propose in this case when you decide about it.
Some solution, and maybe solar panels to charge faster.
Okay. Yeah, I believe you can maybe exchange some information in this regard. Okay, Evaldas, thank you very much. And is anybody has questions to Evaldas? Okay, when there is no questions, then I would also like to announce that there are still some demo trips planned, right, Evaldas?
Yes.
Yes, and when it will be decided which dates, then we will send out the invitations, and there will be some, I believe, some registration scheme foreseen that the boat is not one time overloaded. But you are welcome to stay on board and to see the good things about the pure electric drive. Yes, and generally we are a bit ahead of time, although we were a bit starting later, but still. I thank you all for participation. I hope this was quite interesting and efficient for you. And as I said already, later on I will send to all the participants, at least to all the invitations that I was to the coordinates that I was inviting, the links to the presentations and to this video. And you are also, when you like to contact anybody, there are contacts in agenda, but also you can every time write also to me and I will make forward. So I thank everybody once more and wish you the good end of the summer. Maybe still somebody will be on vacation, or like Daniel now is currently on vacation. And that is also big thanks for him that he find the time to connect, although he's not here. But okay, thank you very much. Wish you all luck and goodbye.
Thank you for the invitation.
Thank you. Bye-bye.
Bye.
Thank you.
Bye.
Bye.
All right.